learned in the prerequisite. Okay. We say we have Pauli matrix. This is very interesting because it was inverted to describe the spin when they have the spin in early maybe 1930 or whatever. There are three Pauli matrix: sigma z, sigma y, sigma x. I would say you really should memorize it if you tell people you know quantum mechanics or quantum computing, right? Their special is that they're Hermitian. What does it mean? Itself equal to its dagger, and its dagger is complex conjugates plus transpose, right? If you multiply itself, you get the identity matrix. Okay, just some characteristic that will help you in the future calculation. Their trace is 0, so they are traceless. What does it mean? You sum over the diagonal, they are 0, right? 0, 1 minus 1 is 0, 0 plus 0 is 0. For this one, I gave you an example, right? Now, these three matrix plus the identity matrix, which is this one, right? Identity matrix, I, of course, you know it is 1, 0, 0, 1. They form the basis of another vector space. So I hope that you won't be surprised because we already talked about it's a linear vector space, right? You have an inner product and you have all these basis states. This basis states now, instead of spin up, spin down, or instead of orange apple, it becomes this matrix. In this vector space is that it is a space of 2 by 2 matrix. Any 2 by 2 matrix can be decomposed into a linear combination of these 4 matrices. Okay, so that is one important message. For example, any matrix can be written as M11, M122, M21, M22, right? And I claim that it can be written as this linear combination. You see that this is just like the basis. I, sigma x, sigma y, sigma z, right? Just like apple, orange, grape, watermelon, right? Or 0, 0, 0, 1, 1, 0, 1, 1, 1. They are not the same. I just say they like them as the basis. And then this one will be some coefficient times then. So it's very convenient. We just say, we usually write this as A0 times I, and this is just a vector product, right? Because if I say A vector equal to AX, AY, AZ, and sigma equals sigma x, sigma y, sigma z. Remember, this sigma x is a matrix, right? When I do this dot product, it's just AX times sigma x plus AY times sigma y plus AC times sigma z, right? This is just like this. I hope you feel that that is okay. It's just like A equal to A1, A2, A3, and then B equals to B1, B2, B3. And we know that A dot B in our 3D space is just equals to A1, B1 plus A2, B2 plus A3, B3. Is that okay? This one is clear, right? Any vector is like this. And that is what we're exactly doing. Except now the B is not a number, it's a matrix. Yeah, question?
Is it an orthonormal basis?
Okay. Now then we need to find out the, actually I don't know, right? We need to find the inner product to see if they are orthonormal, right? And we'll talk about the inner, we can try that later. I forgot if it is. Let's try. That's a good question, right? So now, but one important thing is if M is Hermitian, right? This M can be any matrix, okay? If it is Hermitian, then it is known that from theory, these 4 numbers are real. They are going to be real. Okay, we can decompose into a linear combination of these spaces with real coefficients, right? And this is just to enhance the understanding. For example, if you read the Wikipedia, it says each Pauli matrix is Hermitian. You know what it is? It's Hermitian. Together with the identity matrix I, sometimes we call it sigma 0. they form the basis for real vector space of 2 by 2 Hermitian matrix, right? Real vector space. It's just like in our real 3D, we always have the coefficient as the real, right? And the basis is these 4 bases. Okay? Any questions? So let's continue, and I will answer your question later because I really did not know. Okay? So let's look at the property of the Pauli matrix. One is the so-called, let me see, I don't have many pages. One is the so-called commutation relationship. What does it mean? Commutation, we usually use the square bracket, sigma I, sigma j. This is we say this is a commutation bracket. And what exactly does this mean? It means you want to compute sigma I, sigma j, plus sigma j, sigma I. And what is the meaning of ij? It just says that the I can be equal to x, y, or z. You just take a pair of them, and that is the commutator. Exactly, I'm sorry. I thought that I'm talking about anti-commutation. Should be the difference. Thank you. Is that okay? And what is the result? It is the 2I epsilon ijk sigma k. Okay? So what does it mean? This epsilon ijk is the so-called Levi-Civita symbol. Okay, so basically you say that there are more profound definition, but the way we need to memorize is only this. If you put x, y, z in this order, then you will get 1. If you try to swap them one time, then you will get -1. For example, x, z, y, that will be -1. So as long as you are not in the order, right? So you think this as a circle, right? So if you go in this direction, then it's always 1. But if you go in a different direction, for example, you go with, let's say x, z, y, then you will get -1. Okay, so this is a good way to memorize. You just go through the cyclic order, right? And then you just go through it. If you see that it is actually rotating in another direction, you get -1. If you go through the x, y, for example, you can start with y, y, z, x, you will get 1, right? So let me ask you, what is let's just give any y, x, z. What should this be? It should be -1, yeah? Because you look at this cycle, it's y, x, z. It's going the anti-clockwise direction, right? This you can just try to understand all this permutation. They have deeper theory so that you can have more in-depth. So it's not, but this for 3 of them, this is a good way to memorize. Okay? So what does it mean? Let's take an example. For example, I have this one. Sigma x, sigma y. Commutation bracket, like not anti-commutation. What does it mean here? What is I in this case? I is x, yeah? And then j is y, right? So this is talking about x times y minus sigma y times x. So based on this equation, it is 2i. I is just square root -1, right? So it's a little bit confusing. But then the real ijk is what? What is I? You say is x. And then you have y. Then the last index must be the one you have not seen. So it's going to be z. K is going to be z, right? And then we know that the output is sigma z, right? In this case, K equal to z.
So where does the 2i come?
No, this is the equation. That you can prove it. I just give it, right? When you do this, you will get this one. I'm trying to give you an example to show that it is correct. So let's look at the left-hand side. Left-hand side, sigma x is 0, 1, 1, 0. Sigma y is 0, negative 1, 1, negative I, right? Minus 0, negative I, 0. 0, 1, 1, 0. So, okay? Now, if I try to do a calculation, I try to save the page, but it's not difficult to see this is 0. The first one is 0, right? 0 times 0, I times this one. Maybe I keep the step. I should not jump. Let me just look at the first one. This is 0. And then the second is also 0. The third one is 0. The last one is negative I, right? When I this one times negative I plus 0 times 0, right? Minus, do I get it right? The version is I, yeah, exactly. Thank you. The first one should be I, right? And then the second one will be negative I, right? And then 0, 0. How about the last one? What is this times this one? Plus I, right? So these are the matrix multiplication. What do I get? I get 2I? No. Yeah, 2I, because I minus negative I is 2I. 0, 0, negative 2I. Am I right? Okay. How about the right-hand side? I just want to show that the equation is correct. 2I times sigma xyz. What is sigma xyz? 1, right? And what is sigma z? 1, 0, 0, negative 1, which is equal to 2I, 0, 0, negative 2I, right? So they are the same. Now, I know that that's the way I teach, right? I want to go to the numbers, the details, so that you really understand the equation, right? If you see some equation, you need to do substitution, then it's very clear to you what it means, okay? So the point is this, I give you this equation, right? Commutation relationship. You find that they are not commute. What is 2 times 3 minus 3 times 2? It is 0. But unfortunately, sigma I times sigma y minus sigma y times sigma x is not 0. It is non-zero, right? That is one of the reasons causing this Heisenberg uncertainty principle, because they don't commute. And that is why quantum mechanics is quantum mechanics. If they commute, you don't have quantum mechanics. Okay. So this is the commutation relationship. And the next one I want to talk about is the anti-commutation relationship. So anti-commutation, we use the curly brace. I don't know why I put it wrong in the cheat sheet. And that's interesting. Okay, my cheat sheet have one more example, but I'm not going to go over the example. Sigma I minus, not minus, sigma I, sigma j. Sigma I, sigma j. By definition, it is sigma I, sigma j plus sigma j, sigma I. The only difference is just the plus. This is your anti-commutator. Okay? It is equal to 2 delta iji. Do you understand what it means, delta ij? You know, right? This is the canonical delta. When I equal to j, you get 1. When I not equal to j, you get 0, right? And this is the identity. It's similar to this. It's just that this symbol, the LC symbol, is more complicated. Okay? So I think this is very straightforward. We probably don't need to prove. We don't need to show any example. I don't plan to show any sample, right? You just repeat this, right? So two relationship, commutation and anti-commutation. Any questions? Yeah.
So what's the use of this relationship?
No, this is their properties.
Okay, these are properties.
Yeah, and then later we are going to use them to prove some equation. Okay? So the next property we want to discuss is the trace property. Okay? Let's look at this. What is the trace? Of course, we know what is the trace of the Pauli matrix, right? What is that? I just mentioned. 0. They are traceless. You add the diagonal, right? They are traceless. But how about I multiply them? The trace of sigma I, sigma j. I multiply them. What is that? Okay, what is this? So let's try to find out, right, and try to have some practice on this math. So we know that sigma I, sigma j minus sigma j, sigma I equals to 2I epsilon I j k times sigma k. Am I right? We know this, right? That is the commutation relationship, just from the last line. We also know sigma I, sigma j plus sigma j, sigma I equals to delta I j times identity. Okay? Now I add them together. What do I get? I get 2 sigma I, sigma j equals to 2I epsilon I j k sigma k plus delta I j I, right? So from this anti-commutation relationship and commutation relationship, I add them. Sigma j, sigma I got cancelled. So here I did not write it clearly, right? This should be sigma j, right? Right? Sigma j, sigma I, one negative, one positive, you add them together, got cancelled. Right? That's why I have 2 of this, and these 2 just add together, right? Now let me find the trace of them. The trace on the left must be equal to the trace on the right. What is trace again? You have a matrix. You sum over the diagonal, right? So in that case, this is just equal to the 2 times of the trace of this matrix. 2 matrices multiply together, the constant you can take out, right? Because you can sum them first and then multiply by 2, or multiply by 2 and then sum them. And if I have 2 matrices adding together, their trace must be the sum. The trace of their sum must be the sum of their trace. Correct? Because all these diagonal elements, you add them together first, and then you do the tracing. Or you can do the tracing first and then add them together. They are the same. What is the trace of sigma k? Remember, this is a constant. This is just constant, right? 2I epsilon, a constant. I can take it out. What is the trace of sigma k again? 0. Because sigma k is a Pauli matrix. We say it's traceless, right? So this is 0. And what is the trace of the identity? Yeah, because I equal to 1001. So its trace is 2, 1 plus 1. right? So this is equal to 2 delta ij. Yeah, so you see that the trace of these two matrices equals to delta ij. Right? So what does it mean? If you are multiplying, do I get something wrong again? It's not.
Isn't the
It should,
anti-commutator 2 delta ij?
exactly. That's why I got a 2 missing. Thank you. It should be 2 delta ij, right? So I get something wrong. So I'm sorry for that. I should have a 2 here. Maybe I change it back to red so you don't think that it is extra. So this should be 2, right? So then this should be 4. And then this is 2. Yeah, I got it wrong. Should be 2 delta ij. So if I use j, for example, sigma x squared, the trace of sigma x squared is equal to 2. But the trace of sigma x times sigma y is 0. Now you still don't see the use now, right? It's just for the future math. But that is a good practice to understand all this matrix operation. Is this okay? Now, how is this going to be useful? The topic we're discussing is that every matrix 4x4 can be decomposed into identity sigma x, sigma y, sigma z, right? How do we find those numbers? And this is what I will tell you. The trace of any m, okay, is equals to the trace of A0I, right, plus the trace of A vector times sigma. Because remember, m is equal to A0 times I plus A dot sigma. What is A dot sigma? Look at this again. Basically, what I say that m is equal to A0 times I plus AX times sigma x plus AY times sigma y plus AC times sigma c. Is this clear, right? Again, what I'm talking about is just now a vector. Total vector equal to A times X hat plus B times Y hat plus C times Z hat. But now I have 4 bases in this case, right? And these are just some number. So if I apply the trace to M, it will be the trace of A0I times trace of AX sigma X, right? AXY, right? What is the trace of sigma X, sigma Y, sigma Z again?
0.
0, because they're traceless. So this one is just equal to the A0 times trace of I plus 0, right? But what is the trace of I again? 2. So how do I find A? A0 is just equals to trace of M divided by 2. Okay, so if you give me a matrix, I can find out its component by finding the trace of the matrix divided by 2. Then that is the component of the identity matrix. Okay? It's just like I'm finding what is the X hat component. Then how do I find AX, AY, and AZ? I know, sorry, it's a bit messy, right? 1, 2, and then I go to 3. How do I find the AX, AY, and AZ? Let's consider this. The trace of M times sigma k. And actually, I want to use sigma k times M because that will be useful. They are the same because of the property of the matrix. But what is sigma k times M? Okay, that is the hint. Let's take a look. This equals to what? equals to the trace of sigma k, right, times m, right? So it is going to be A0 sigma k times I plus AX sigma k times sigma x plus AY sigma k times sigma y plus AZ sigma k times sigma z. Do you see what I'm doing? Again, m is just A0 times I plus AX times sigma x plus AY times sigma y plus AC times sigma c. I just multiply sigma k from the left. I want to find out what is sigma km. Is this okay? Any questions? Yeah.
Can you explain the third point again?
Can you say again?
The third point.
The third point, right? I only try to show you this. I want to find the trace of sigma k times m. Sigma k can be sigma x, sigma y, sigma z. And this is a matrix, right? Which is one of this matrix. And one of this matrix multiplied to the m that I try to decompose. And you give me any m, right? 1, 2, 3, 4, it can be 1, 2, 3, 4. I just want to know what is the trace of this one, because I know that you don't know, because I read from textbook, I learned it. I know this will help me to find AX, AY, AC. But now I want to find what is trace sigma k times m. M is just A0 times I plus AX times sigma x plus AY times sigma y plus AC times sigma c, right? Make sense? And now I multiply sigma k, just distribution law. I prepend to the left. That's what I have, right?
Professor, and M is Hermitian?
Or M doesn't have to be Hermitian. Yeah, it can be general. But we say that if it's Hermitian, A, X, Y, Z, they are real. So then, let's look at this. What is the trace of this one? What is sigma k times I? Sigma k, right? Anything times identity is sigma k. And then the trace of sigma k is going to be 0, because it's Pauli matrix, right? So this is 0. How about what is sigma k times sigma x? That now depends, right? So this is a little bit general. If, for example, if they are the same, what do you get? It's just 2, right? If they're the same. If they are different, then you will get 0, right? Because k is here, x, y, z, right? So basically, you just substitute, just find an example. Let's say k is sigma x, right? For example, how do I say it? This one is going to be 2 delta kx, 2 delta ky, 2 delta kz, due to this equation. Okay? So only one term will left, right? And that is the term that is the one I want to look for, right? Is k. So basically, then you will find that the trace of sigma k times m equals to 2ak, equals to 2ak. Right? K can be x, y, or z. Right? For example, when k, let's be very careful, when k equal to x, let's say I'm finding sigma x times m, when k equal to x, this is equal to 2. And these are going to be 0. Right? So sigma x m equal to 2ax. So in summary, ak equals to 1 over 2 trace of sigma k times m. So if I give you a general 2x2 matrix, you can decompose it into the component A0 AX, AY, AC by using this equation. It's not very clear now why we want to use this, but it will be clear soon, right? Any questions?
Later you're just sort of decomposing into Pauli rotations, X, Y, and stuff.
You can say that, but because it's addition, right, it's not useful, right? Because when you want to decompose an operator to different rotation, you actually want multiplication, right? One after one. This is going to be used in density matrix that we will discuss after this Pauli notation, Pauli matrix. Now, then we go back to the inner product. You just asked me whether they are orthogonal, but I did not think about that, right? Let's just review a little bit, right? What is the inner product of a matrix? First one is the inner product of a vector. Let's review. We spent some time to discuss this earlier. The inner product of a matrix of a vector A to B, right? We say that, okay, if I put in the matrix form, it's going to A log star, A1 star, all the way to AN minus 1 star, times B1, B0, B1, all the way to Bn minus 1, and this gives us A0 star, B0 plus A1 star, B1 plus all the way to AN minus 1 star, Bn minus 1, right? I know I'm very fast, but you should be able to understand what I'm trying to say, although not following each digit. Is that okay? Okay? This is the inner product. But besides this, we say inner products fulfill some laws. We can define the same inner product for matrix. And let's just concentrate on the 2 by 2 case, but in general, I can just write it A, B. Both of them are matrix. It's just up to me to define, right? As I told you, I can define inner product of English, that the common spelling, apple and apples. I can define that their inner product is apple, A-P-P-L-E. S is not common, right? Oh, of course, if I keep deriving, you find that it doesn't work as the requirement for inner product, maybe, right? But I definitely can define inner product for anything as long as it fulfills the definition of inner product. So we won't go into those details. You just trust me that it works, okay? I just want to relate this to this. Remember, we can use the inner product of the basis vector and a vector to find the components, right? We can use either the projection operator or just find the components. For example, do you remember, for example, when psi equal to A, let's say alpha alpha 0 plus beta 1. I want to find the component of 1 of 0, right? To find alpha, which is the component of 0. What do? I use inner product, right? 0 inner product with psi. And then what do I get? Alpha plus beta. Make sense? This one, everyone okay? Distribution law. What do I get? Alpha. That's what we did, right? The inner product of the vector is this, of the matrix is this. Equals to the trace of, let me see, A star times B. So the first matrix, you take the complex conjugate, you multiply to the second matrix, you take the trace, that is the inner product by definition. If you watch the previous video, we already said that it's up to us how to define, right? This is a useful definition, right? So do not argue why you call that an inner product. You can define yours as long as you satisfy the requirement of the inner product in the linear space, okay? So that is the definition. So now, I just want to ask you, for what we did earlier, we have M, recall? Right, so this one we are not going to prove, right? Just take it for granted. Inner product of this, right? Just recall we just learned. M equal to A0I plus AX sigma X plus AY sigma Y plus AZ sigma Z. Just like psi equal to alpha 0 times beta 1, right? How do I get the coefficient? I do an inner product with the basis, right? So, what is the inner product of I times M in this case? It's just equal to the trace of I star times M, correct? By definition, inner product of A and B is just the trace of A star B. I times M, right? What is that? Of course, it's just equals to itself, right? Now, but here you see that it's not exactly, but we can actually, you will find that A0 actually equal to 1 over trace of M. I actually can, although I define in this way, I can actually define the inner product as 1 over 2 trace. Again, it's just a scaling factor, it's up to me, right? But I still use the conventional one here. But the reason I wanted to tell you is that this makes sense. No, this is not, I'm sorry. A0 equals to this one, right? So this is just like the inner product of I, M. Do you see that? I want to find the coefficient in front of 0. I do the basis to the whole vector. I want to find the coefficient in front of I do the same thing. The basis is I to the whole matrix. And then I get the A0. Let me write down another expression, right? How about the sigma K M? Again, the inner product is the trace of sigma K star M equals to this one. Why I can say that? Why the sigma K complex conjugate equal to sigma K? They are what? Unitary. Say again, is it unitary? What do you call it? Hermitian, right? So I can write that, yeah? And I already told you that the AK equal to 1 over trace of sigma Km, and this is just 1 over the inner product of sigma Km. Okay, let me recap. I think it can be confusing. We say that the inner product of this is just an analogy. Right? You don't really need to agree with me. The inner product of a vector is this. I can define the inner product of a matrix in this way, the trace of their product. You need to trust me. It works, right? This is the definition. That's it, in definition. And why it's useful? Think about that. I find the components of a vector, of a basis. I will just do the inner product of the basis with that vector, then I will get the component. Isn't that in this case, in order to find the components, I need to find the trace, but turn out it's just the inner product. So again, I'm using the inner product of the basis with the home vector. This is still vector, I mean, not the matrix vector, okay? Yeah, you need to agree with that, right? That the basis is a matrix, but the whole thing is still a vector of matrix, yeah.
So why go to this formulation if you can just take the matrix and split it into its basis vector? And then now you're down to these vectors and you can do inner products of the vector. I guess like the example you're showing.
No. Here we are not using any vector. They are still matrix. I'm just using this to show you that the basis times the superposition, you do the inner product, you will get the coefficient. Let's do not call it vector because I think now some of you still don't know what I'm talking about exactly. Let's call basis state and superposition. If I want to find the coefficient corresponding to a basis state, I do an inner product of basis state and the superposition. Then I get alpha. What I'm trying to here is this is the basis state and this is the superposition. Although they are matrix, but this is the basis. Don't talk about vector now. It can be confusing, right? There's a matrix, 2 by 2, there are 4 numbers. I want to find the components, the coefficient of this component. What I'm showing you is that we prove that it's just equal to the inner product of the basis and the superposition, right? Yeah, question? AK, K can be X, Y, Z.
A0, X, Y.
No, because this equation is for X, Y, Z. A0 I show here already. A0 is I times M. You can call it sigma 0, however. So you can combine everything to call this sigma 0, erase this 9, and then now your K is 0, 1, 2, 3. Yeah. So some textbook use 1, 2, 3 instead of X, Y, Z. Yeah. Okay, so friends, for one of your classmates' suggestion, I actually did make a mistake about the definition of the matrix inner product. This one is actually not the conjugate, it's the conjugate transpose. So I better just put dagger, okay? So this one should be dagger instead of transpose, right? So A dagger equal to A complex conjugate followed by transpose. Okay, so I was wrong about that. I'm sorry. So this is dagger. So this is dagger. And because it's Hermitian, then now it is correct because if I put the complex conjugate and transpose, then after I did a complex conjugate, the sigma y becomes this, and then I do another transpose, it becomes 0, negative I, 0. Okay, so it is correct now. Thank you.